Hello, everyone, and welcome to this special, well, basically fireside chat here at CosmoQuest. Now, while I could be sitting beside my fire, I didn't set up to do that today because I want to be able to bring you the best production possible while we talk to Carver Bierson about his work exploring Pluto and the possibility that it had an early ocean shortly after it formed. Now, I'm going to bring him on. We're going to have some questions from you as we go. And I have images and so many different things. And Carver is our first guest as we work to stretch the capabilities of what we do here at CosmoQuest. So I apologize in advance if we drop audio now and then or something goes slightly sideways. Now, I don't actually expect any problems, but that means we are guaranteed to have some. And the reason I'm looking sideways right now is I want to make sure that I actually have his audio in all the right places before we go ahead and get started. So feel free to ask questions. As always, precede your questions with that purple circle with a purple star in the center to make it easier for me to find them. And, well, here we go. Hello, Carver, and welcome to CosmoQuest. Um,
Thank you for having me.
I read the title of your talk. I was excited to get to hear about it, and then LPSC got canceled.
Yes, well, I think everybody's very sad to not get to see everybody and listen to all the wonderful science, but it's great to be here. So,
So how many times have you gotten to go to LPSC in the past?
uh, about 5 or 6 times.
Yeah. So
So,
this is for those of you out there who don't know what the Lunar and Planetary Sciences Conference is. This is my favorite conference of the year for three very important reasons. The first is they actually have talks that are long enough that you can learn things, that the scientists can actually explain their ideas and do them justice. The talks are often 20 minutes long, and they're arranged in a way to tell a story through the session. So there's often an overview on here's the big picture of our mission. And then they work through the pieces. And as an astronomer, these conferences are why I know anything about planetary science. Now, the second reason is they actually have break periods that are long enough that you can talk to people, build collaborations, and it's all crammed into one giant hotel conference center. And so you all end up hanging out at the bar, well, meeting the colleagues that you don't know you're going to have in a few years. And then the third very important reason I love this conference is it has infinite coffee. There is always coffee, always coffee.
an important part of any meeting.
It is true. Now, you were part of a session called Ocean Worlds. And you were lucky enough to even have been chosen to give an oral in the first slot of that session. And that is like the gold star on the forehead place to be. Now, what was the talk you were all prepared to give?
Yeah, so I was excited to tell everyone about some work that I've been doing with my collaborators, trying to understand when Pluto got its ocean. So, kind of for some background, we think that Pluto has an ocean today, or at least there's some circumstantial evidence for that. And mainly, if you pull up an image of Pluto, there's this big circular feature right in the center of that image, Sputnik Planitia, which is a big impact basin filled with nitrogen ice. And the location of that basin and most basins throughout the solar system we see tend to end up near poles of planets because there's less mass there than you would expect. But this basin's near the equator, which indicates that there's more mass there than expected if Pluto's reoriented itself. And the only way to really do that is if there's a subsurface ocean kind of supporting it from beneath. And if there's an ocean today, it raises this question of when did that ocean get there? And that's kind of the thing that we're trying to explore in this work.
Now, you're just a graduate student, by which I mean you've spent several years being tortured and becoming an expert in your field. And you have had the glorious not having to go to committees duty of the rest of us. But you're still just a graduate student, which means people are going to say you're just a graduate student. How did you get everyone's attention to say, starting several years ago, this is what I want to explore, and what has been the process of working to, well, either prove or disprove the existence of a potential early ocean?
Yeah, so I started as a grad student right before New Horizons flew by Pluto. So my timing
Perfect
was very good.
timing. Yeah.
Yes. Um, and that let me just kind of start on that very early on. Um, Initially trying to, look at the images, look at the data, and then quickly start modeling and try to figure out, is this at all reasonable that there was an early ocean on Pluto? So building numerical simulations of Pluto's interior through time. And one of the things we found was that just the heat from radioactive decay of long-lived species like uranium through solar system history is enough to get an ocean in Pluto's interior and maintain it to the present day.
Now let's break this down a little bit and talk about what this means. Now, our own planet is warmer than it should be if we were only getting hit by sunlight. And the reason for this is we've got all sorts of radioactive stuff, some of which causes radon in your basements. So if you live near granite, get your basements checked. And this radioactive decay in the process of breaking down atoms into different atoms and releasing other particles, it also releases heat energy. Here on Earth, this is part of why we have a liquid core, as well as the fact that we're really big and haven't cooled off yet. Now, we look at Mars, though, and Mars is way bigger than Pluto. It's cold. How is it that you end up with something in the outer solar system that is smaller than Mars and still warm on the inside?
Yeah, so there's two parts of this. One is that what you mean by warm is relative. When you say Mars is cold in the interior, we're talking about cold for silicates, which have a much higher melting temperature than water ice. So Pluto is certainly still plenty cold enough that all the silicates are very solid. But the other thing is, how are you getting your heat out is a big question as well. The Earth gets a lot of its heat out through convection in the Earth's mantle, which is very efficient. And for Pluto to have this ocean today, it probably has had to be pretty inefficient in getting its heat out. So not, the ice itself had to be just solid and just slowly conducting heat through not convecting at all.
And that's a slower process where convection is essentially that lava lamp process, the granules on the sun process. It's a physical rising, giving off heat and settling back down. Whereas conduction is more like a photon going, okay, I'm trying to escape. I'm trying to escape. And these individual photons are taking that energy and carrying it away in a slow and miserable process. Is that fairly accurate?
Yeah, I'd say so.
Okay, again, astrophysicist here. So you've been working to do numerical models. What all goes into doing that other than I'm guessing a whole lot of Python?
Yes, so I tend to blend Python and even Fortran to try and get some extra speed out of things when necessary.
Right.
Um, but it's essentially taking our equations of heat. So if you bring up the image of, I think I called it the cold start, the thermal model through time. Here, there's a brown line, everything beneath that is the interior Pluto warming up from those radioactive elements.
Okay.
And
So there's a couple of different images. Let me make
yes, that will work. Um, that'll work. So in the upper left, there's that colorful figure there. Um, and the colors represent temperatures. So your warmer colors are warmer temperatures, which are more towards the interior. And there's a black line which is tracing the top of the ocean. And so that ocean, grows through time and then it cools off. And the focus of this study that I was going to talk about at LPSC is the difference between what happens if Pluto started with an ice shell initially versus what happens if Pluto started with an ocean. And can we go and look at the data and tell the difference between these two kind of end member cases? I'm saying, so it is just a difference in phase. I'm saying starting with, uh, sorry, starting with either a solid ice shell on the very top and liquid beneath that, or just solid ice all the way through. And the key point here is that ice, when it freezes, is buoyant, right? It expands. This is why the frozen ice sits on top of a lake. And so if you started with a bunch of liquid water and refroze that ocean, it's going to want to expand generally. And we can look for that in the tectonics of Pluto's surface. We can look at the cracks on the surface and see, does it look like Pluto's ice shell was expanding through time? Or is it the opposite? Did it start with an ice shell that was melting, and so the whole thing was compressing early on, and then later transition to refreezing and then expanding?
So, what did you find?
Well, our answer isn't totally clear, and we're not totally done here. But when we're looking for this, the biggest difference is very early on. And that's when our geologic record is the most incomplete and the hardest to look at.
Of course, of course. Isn't that the story of science?
Yes, everything's really degraded. So we're looking, do we see anything in the oldest terrains on Pluto that look like compression? And for the time being, it looks like no. We don't see that evidence of compression.
But
So do we see?
you found faults.
Yes, we do have faults, but they all look to be extensional.
So
Everything
so what does extensional faults tell us in this story?
that an ocean was refreezing, so things are cooling off. And the ones that are being shown here that are pointed out by the blue arrows look to be at least relatively young, looking at how they're cross-cutting craters and other things on the surface. Um, so, it looks like the surface is kind of pulling apart from itself as everything was
And the
expanding
fault is
outwards.
just anywhere on a surface where whatever geological things are taking place causes that surface to basically become faulty and break. So we have fault lines in California where earthquakes have shattered the surface. And on Pluto, these fault lines are related to its water driven geological processes.
Yes, among other things, anything that's creating stress, you're going to have things like tidal stresses from its moon Charon as well. So, here on the Earth, when we think about tectonics, it's all plate tectonics because that's the main geologic driver for the surface of the Earth. But Pluto doesn't have plate tectonics, so there's all these other processes generating faults. Refreezing of an ocean, impacts can also create stresses and faults nearby, things like this.
All right. So I keep taking your story out of order. Let's try and put all the pieces together now. Like I said, I was really excited to hear your talk. Um so you started out with this, all right. So, what if it started with either a liquid ocean all the way out to the surface, or it started out with ice, and you ran numerical models that built in a set of languages we shall not speak of again. You look to try and understand how the processes of radiating away heat to space would drive expansion and contraction as essentially a war against each other. So how many models did you run? What factors did you have to take into to consideration? And what predictions did you have to go then looking for in the imagery of Pluto?
Yeah, so the nice thing about this sort of process is everything's very kind of first order, kind of back of the envelope almost. If you're refreezing an ocean, kind of regardless of how fast that happens or exactly what the details are of how quickly Pluto's getting out the heat, the ice shell's going to expand. And the same is true of the opposite. So if you're, um, taking an ice shell and melting it, things are going to compress. So we don't have to worry too much about the nitty-gritty details of exactly what the time scales were, because we can't measure those things at Pluto anyways.
Right.
We don't know exactly when anything happened. So when we go to the data, we're looking for, do we see evidence of compression? Do we see evidence of expansion? And when do we think these things happened? And that's still an ongoing process of going through that data and trying to map out all these features and put together a timeline. And lots of people are working hard on this. But we see some old, degraded fault structures that seem to hint, at least, of early expansion on Pluto, which means that maybe Pluto did start off warm. Maybe it started off with liquid ocean really early on.
And in trying to understand this, you did some. I love how these files ended up inadvertently named. You have pi melting, pi freezing. You're doing to pi graphs things that one should not do to actual pies. Can we talk about how you basically modeled, for instance, with freezing? What are the kinds of things one might expect to see that is causing uplifts and crevices, for instance?
Sure. So this is just a kind of cartoon drawing of the processes involved. So as I've been saying, as you're refreezing that ocean, so your shell is going on, you're going to expand, and you see at the surface what looks like things kind of pulling apart from each other as it's growing outwards, essentially.
And is
And
this
so those
something we see happening on Earth at all?
there are certainly regions on the Earth where we see extensional faulting. So classic one is like basin and range, kind of east of the Sierras. You see extension, um, and many other examples I'm not going to be able to think of on the Earth off the top
That's
of my head.
okay. That's okay. These are the kinds of questions I don't mean to be inadvertently giving you an oral exam. Um, now pie melting is I your poor extensional areas are now sloppily falling sideways. So what happens over time in these systems?
So this is the opposite case when you are melting an ocean and basically the top surface has to fall down because there's less volume beneath it now. So everything just gets shoved up on top of each other,
Okay.
which is how you build these kind of folded complexes, and might see like mountain ranges or things like that built in this way.
And if you'd seen this would have again been which of the cases? Oh, Zoom just froze.
So this would have been for a cold start. We would have seen that early melting causing some early compression. And it's possible that as this ocean was refreezing later on, that would have then kind of relaxed away as things started to expand again. And so that might erase some of this evidence, or other processes might have erased some of these features if this happened really early in Pluto's history.
And then we have the pi Ocean, which looks like a massive crater. But what's actually being seen here?
Yeah, so at the surface, you do have a massive crater, and that's meant to represent Sputnik Planitia, the big basin on Pluto, filled with some nitrogen ice there. And when you have a big basin like that, one of the ways that a world wants to support that is by having the material underneath kind of rebound. Um, this is the same process that causes icebergs to have most of their mass under the ocean to support the weight of what's above. Only this is kind of the opposite. Because you have a big hole in the ground, you need a more dense material to come up and support that missing mass, essentially,
Okay.
at the surface. And this is why we think that Pluto has an ocean, because this gives the more dense water, brings it closer to the surface. You get a mass excess there, and that causes that part of Pluto to rotate towards the equator.
And and that is one of the really cool things about Pluto that I don't think gets communicated out to the public enough. And I don't even think enough scientists think about this. When we look at Pluto, the orientation of this world has been altered by the structures on its surface that torque it around, thanks to the fact that it has this fabulous little moon.
Yes, and this is a process that I think acts throughout the solar system. In general, where you see like big, massive features that tend to be near the equator. If you think about Mars, you have big Tharsis bulge, which is a huge mass excess, and that's also very close to Mars equator. So this is a process called true polar wander, basically planets reorienting themselves to get into like a minimum energy spin state. And it can tell us a little bit about how they've evolved, and we look for stresses associated with this too to try and confirm that it's happened.
Now, you had, I don't know if it's the fortune or the misfortune, to have to dig through all of New Horizons' amazing imagery of one and only one side of Pluto. Um, we've seen the rest, just not at high resolution. Um, and trying to see if any leftover signs of your science results were lurking under the, well, more recent activities that we've seen. And you've already mentioned that the faults that I showed earlier, well, those faults appear to be fairly young. And can you explain just how it is that you tell what's young and what's old? Not the when, but the relative ordering of formation features, feature formation on Pluto.
Yeah, absolutely. And of course, like one important part of this is that with New Horizons and any of these missions, right, there's a big team of people
Oh yeah.
all working together on all of this stuff. So it's certainly not just myself, and I've got a lot of help from a lot of great collaborators in this. And in going through these images and trying to look at the age, one thing we look for is how pristine do things look. We see some faults that look more degraded, so smoother edges, things like this. It looks like more landslides have
How do they
occurred.
get degraded? So there's landslides. What other things affected? I know with the moon, there's that rain of micrometeorites. I don't know if there's micro icy bites hitting things out at Pluto.
Yeah, it's certainly a very different environment at Pluto, and I'm not sure we totally even understand exactly how many small bodies there are hitting Pluto. That's one of the things we've slowly started to piece together in the last few years, is understanding maybe there's a lot less small stuff
And it's totally
actually
all
out
right
there.
not to have answers to my way too many questions. We have, I mean, what year did we finally fly past Pluto?
2015.
Yeah, so it's been less than 5 years. Heck, it's like three, four and a half at this point.
And we took more than a year to get all the data down to the
Yeah.
ground as well.
So there's going to be so many things that you can just be like, yeah, we don't know yet. That's cool.
And that's certainly the kind of the case here. That's kind of what I'm getting at, is that we're still learning, what are the processes involved? What are the
Yeah.
processes shaping Pluto's surface? What is the thing that explains these faults that we're finding? What's the history of Pluto's, expansion and contraction? These are all big kind of first order questions that we don't know yet and we're working on.
But it sounds like fundamentally one of the best ways that you figure out what happened most recently and what happened most in the past is how things are layered. A crater on top of a fault, the crater's newer. A fault on top of a crater, the fault is newer. And you have infilling process. What are all the different processes that you see layering on top of each other?
So we see impacts, we see these fault features, and we also see lots of volatile species that are moving around on Pluto. So you have methane ice on the surface, but it's also making up the atmosphere and freezing out. Methane is doing the same thing. So we see methane coating peaks in some areas and other places where it looks like methane ice is maybe being eroded away.
So, this
And
is a process like frost forming in the morning where these gases fill the atmosphere, and then as the temperature drops, they come out of the atmosphere and coat the surface like frost coating the grass at night.
yes, but here on the Earth, we only have water doing this. On Pluto, you have nitrogen, carbon monoxide, and methane all doing this together in different places at different altitudes. And so you get all these different mixtures and colors, textures.
And that is why Pluto is so stunningly beautiful. And I have to give a shout out to Alex Parker here because he has done some of the most gorgeous renditions of Pluto and Charon, stretching to bring out different colors, done to make it look like it would for the eye. So go check out Alex Parker's Twitter feed to catch, well, random bees, as well as all sorts of amazing images of the worlds he's had the opportunity to explore. Now, we have a question coming in from Gildastar, and he's asking, how much bandwidth did New Horizons have to get data back to Earth?
That is a question I'm not going to know the answer
No, that's fine.
to.
So if I remember correctly, it was less than a 2400 baud modem. I don't remember the exact number. I remember it was less than a 2400 baud modem because I was like, holy expletive Batman. I remember being angry about trying to look at the Shoemaker Levy 9 images over a phone connection. And here they are with fewer bits trying to look at high res images of Pluto.
Yeah, so I remember for the Arakoth encounter, which we did last year,
Right.
our download rates were something like a kilobit per second after the encounter.
Dang.
So we'd get, pieces of the image and then we'd wait and then we'd get another little piece of the image and wait.
Yeah, this is science that requires delayed gratification.
Yes.
So, going through the images, I'm going to keep going back to this question because I keep distracting you. You went through all the images looking for things piled on top of each other, looking for random bits of surface that were older. And this is a problem we have on the Earth. This is a problem we have on every world. Like here on Earth, if you want to see old rocks, you have to go to Western Australia or parts of Canada, and everything else is new. And so here you were going through Pluto trying to do the same. And what was that process and what did you find?
So, in general, we find that it looks like the surface is consistent with there being an early ocean on Pluto, at least tentatively. And this is very much, but it looks like maybe it was this early ocean. And so we're trying to put together how might this ocean have got there? And why was there an early ocean on Pluto? Is this a crazy idea or not?
And the is this a crazy idea comes from the fact That there is no logical way to justify having liquid at that temperature and pressure at the surface of a world.
Yeah, for context, Pluto's surface temperatures are like minus 400 degrees Fahrenheit. So it's
Yeah.
very cold.
Yeah. So how do you justify a liquid ocean at these remarkably cold, low pressure places?
Well, one way this might have happened, and this is kind of the way that we prefer, is that just as you're putting Pluto together, you have a lot of impacts. And
Yeah.
impacts have a lot of energy in them, and they can really warm things up.
So this is velocity getting transformed into heat.
Yes. So what you're doing is you're taking all of that energy as you're smashing everything together. And the question is, how quickly can you get rid of that heat? So if you form things really fast, you hang on to it in the
Mhm.
interior and you warm up a lot. Whereas if you form really slowly, really gradually, you just kind of gently radiate that heat out to space and you can stay cold
Can
the
can
whole
you
time.
put can you put orders of magnitude on what fast and slow mean in this context?
Yeah, so it looks like if Pluto formed faster than about 30,000 years,
Okay.
it should have formed hot. And if it forms slower than that, on millions of years timescales, then it should have formed cold.
Okay. And there's papers out there that are saying Jupiter could have formed in 300,000 years. And Jupiter's a hell of a lot bigger than Pluto.
Yes, Jupiter is also forming through like very different processes
Right,
than
right,
Pluto.
right.
Uh, so, but this is nice in part because other groups have been working on how did Pluto form over the last 10 years. And one of the things that they've been moving towards is this idea that maybe Pluto and its neighbors in the Kuiper belt formed by getting basically collections of particles together in the outer part of the solar nebula and then undergoing gravitational collapse, which is
Okay.
a very fast process
Yeah.
that could have happened on the timescale of hundreds of years. Um, and so it looks like we're kind of converging on this picture of these worlds formed quickly and maybe formed with this really active kind of geology on them very early on that's since largely kind of frozen out.
And this gives us a picture of an early Pluto that was essentially left out on the windowsill of the solar system to cool after forming through this immensely violent process that left it hot and teeming with oceans and chemistry that is now fossilized in its structure. And just the idea that we could have, for this brief period of time, had an ocean world 5 light hours from the sun is kind of amazing to think about.
Absolutely. And I think one of the things that's really exciting about this too is that Pluto probably wouldn't be the only one. You have other large Kuiper belt objects, worlds like Eris or Neptune's moon Triton, which is probably a captured Kuiper belt object that probably formed in similar conditions and would have had their own oceans.
Eh,
Maybe still do. Who knows? We
Yeah.
haven't visited them.
And I don't expect you to know the answer to this question necessarily, because the field of science is huge and I'm about to wander off into exoplanets. Is it possible that we're going to be able to look at systems with like the Atacama Large Millimeter Array and understand even in better detail just what might have happened with Pluto by seeing snapshots of other solar systems in the process of forming?
I hope so. Uh, I think the images that we're getting from ALMA of these beautiful gas disks around other stars, different points in their own histories, is telling us a lot about the processes that happen during solar system formation across a whole range of different conditions. And it's really exciting. it's something a little bit outside of what I do, but I follow it with enthusiasm.
And I originally planned to only keep you for 30 minutes. We're coming up on 30 minutes. Now, I'm not going to just kick you off the screen. I'm going to instead say, so what haven't I asked you that I should have, that you're just dying to share because it's so cool and you wish you'd been able to present it in that amazing slot that you had at LPSC before it was canceled?
Um, I I just think this is a wonderful story of trying to understand like the kind of the deepest time of our solar system using what very little information we have. We had one flyby of Pluto. We got good images of less than half its surface, and trying to recreate its early history from that has been an adventure and one
Yeah.
that I'm excited to keep working on.
And what is so awesome about your career is you started this just as we were getting to Pluto, and you're young enough that you can be a leader of a mission to the outer solar system and still be in the prime of your career when that spacecraft gets there. And planetary science is all about delayed gratification, waiting for our missions to get to their worlds, starting to build them decades before they actually lift off. And I hope that you get to keep exploring these icy worlds, whatever they may be orbiting, Sun, Neptune, whatever. If if you had anything that you could tell someone watching this video right now about becoming a planetary scientist, about what you're hoping to have discovered, anything, what do you want to share?
Uh, I'll just say that I think it's a really exciting time in planetary science right now, especially with upcoming missions like Europa Clipper and JUICE from the European Space Agency going to the Jupiter system. We're going to learn a lot more about ocean worlds and how they work and how different they can be from one another. And I'm looking forward to all the surprises that come from that.
This has really been awesome, Carson. I know our audience is just out there drinking this in quiet. Do you have time to hang out a few more minutes and answer any questions they may have?
Yeah, absolutely.
Okay, sorry to keep you late. Um, so Paranor is asking, is there modeling planned on the heat gradient of the solar system at ignition? I'm guessing ignition of the sun, with the possibility of a liquid ocean on Pluto.
So there are certainly many groups that look at the disk temperature as the solar system's forming. And some of that heat in the disk comes from the sun. Some of it also comes from actually dissipation within the disk because it's a
Friction.
fluid moving around. Yeah, so there's frictional heating
Yeah.
within the disk itself that can warm it up. And heating from cosmic rays and sources outside the solar system also matter for this. Uh, so yes, there's lots of groups thinking about this, and this is an area where in the past we haven't had much in terms of constraints, but with ALMA and all these new observations of disks around other stars, I think it's a field that's learning a lot very quickly, and um, hopefully we'll understand a lot more about these processes in 5 or 10 years.
And what I love about our complete lack of complete understanding of how solar systems form is different groups are piecing together different pieces of understanding. So you have the outer disk is expletive cold, but individual objects can get massively heated up through collisions, which is what you're working on. We have the inner solar system that's getting baked dry as everything gets pushed outward, but then getting inundated with water through collisions. So the story of our solar system is basically one of let's just throw stuff in all directions, see where it lands, and see what physics that causes. And trying to figure out all those moving objects, well, it makes herding cats look easy. Now, what other questions? Do we have any other questions out in the audience? Hello, Fedmil. Hello, AstroWise. I see people waving at each other out there. I love the comment. We love surprises, as long as they're nominal surprises.
Yes, as long as the mission works and we're learning about the bodies.
Order always resolves from chaos. Sometimes order resolves into chaos. That is also a thing. So I think everyone is just sort of pleased and full of science and ready for a nap.
Excellent.
Gildestar asks, if you lead a future mission, are you going to make sure you get images of both sides of the object? And thank you, Fenmil, for the bits.
Well, I will say for Pluto, we did get images of both sides that are
high res,
just not high res. And really, the problem with the outer solar system is New Horizons was one of the fastest spacecraft we've ever launched, and it took 9 years to get to Pluto.
And how fast was it going, if you remember?
It's like 10 times faster than a bullet. It's some absurd number like that. So if you want to stop and go into orbit to get high res everywhere, you have to go slower and a lot slower.
Or have a whole lot of fuel you carry with you, which is a completely different problem.
Yes. So in the outer solar system, it's very hard. I think if we want an icy world in the outer solar system that really image well, the best is probably Triton.
Yeah.
Because then you can go into orbit around Neptune. Neptune's got a lot more gravity to slow you down. And we could really do a detailed, careful study.
Yeah, you still have to carry fuel, just a lot less.
Yes.
You essentially accelerate as fast as you can and then slam on the brakes when you get to one of these worlds. And the only way to slam on the brakes in space is to fire a rocket. Or slam into the gravity of something else, which if done wrong ends poorly.
And it's not always easy to get right. Many spacecraft have missed trying to get their orbital insertions just right, and it doesn't go well.
So Gildestar responded, "He's young. There's time to get into orbit." All right. So I think that's all we've got today. I really hope I do get to see you giving that honored first slot in an oral session someday in the future. And I'm so glad that you were able to come on today and give us a taste of your science. So what are you going to be focusing on now that you're trapped in your house?
Well, currently I'm trying to wrap things up, be graduating soon here, hopefully, and moving to hopefully start working with NASA's Psyche team and start new projects on that.
So you have asteroids in your future.
Yes.
Well, we are all about the asteroids around here, and I hope we get to follow your career into the future. Thank you so much for being with us, Carver. And if people want to follow your research, where should they go to look?
I am not on social media, really.
That's okay, but you can point them at the New Horizons website.
Yes, that is an excellent place to go.
So everyone, if you want to follow along with what Carver is doing and with what the rest of the New Horizons team is accomplishing with this amazingly slow downloaded but wealth of data that they've gotten, go check out the New Horizons website put out by the Advanced Physics Labs at Johns Hopkins. That concludes our coverage for today. We will be back tomorrow. I am going to temporarily replace you, if I can, with our schedule for tomorrow. I just need to find where I hid the website. We are working to update our websites to include more and more information on how you can, well, fill your time with a bit more science as we work to deal with, well, the way too much time on our hands for so many of us. So, if you go to the CosmoQuest website, you can find that we have a ever updating schedule of events. Tomorrow is Wednesday. It's going to start at noon with our regularly scheduled Rocket Wednesday, brought to you by Annie Wilson. It's currently a slow rocket world out there, so that may go brief, but following that, we're going to have scientists on to talk to us about Mars runoffs. Yes, folks, that is water running on the surface of Mars, and the possibility that Venus today has a magma ocean. Let the science flow. We are here to bring it to you right here on CosmoQuest X, only on twitch.tv. Now, if you want content to fill your hours between our streams, join us over on Discord. We have a variety of volunteer projects you can join. We have a Games and Gamers channel where you can find a buddy to play a game online. And we just yammer at each other as we're all, well, working from home. So let's get through all the things that are going on together, and let's, well, keep our world filled with science, because science is how we're going to get through to a better tomorrow. So this has been this special interview segment of the Daily Space. I am your host, Dr. Pamela Gay, and this episode will be produced by Susie Murph. We are a product of the Planetary Science Institute, a 501c3 nonprofit dedicated to exploring our solar system and beyond. We are brought to you by you. So thank you for your subs, your bits, and your patronage at patreon.com/CosmoQuestX. So wherever you are in the world, I'm going to try and find someone to raid with this stream so the science can keep flowing. But for now, I want to tell you that, well, we're going to get through this together. And for now, just get out there and have a great morning, evening, or afternoon in isolation. But you have the internet. So have a great morning, evening, or afternoon, and get out there and wash your hands. Bye-bye, everyone.